Hi everyone, myself Sunil Mandal. I'm a PhD scholar of NIT Surathkal. I'm pursuing PhD degree under the guidance of Dr. Raju Prabhakaran. My paper title is A Novel Multi-Stage Ultra-High Gain DC-DC Converter with Active LC2D Network. My content consists of introduction where I will be discussing about basic high gain DC-DC converter and why we require high gain DC-DC converter, and I will also classified high gain DC-DC converter isolated in non-isolated couple type of high gain DC-DC converter and so on. I will also discuss advantage in isolated, disadvantage in isolated, why require non-isolated converter, then background and motivations for developing the high gain DC-DC converter in the area of non-isolated high gain DC-DC converter. I have proposed novel topology, and I will be also discussing derivation of the proposed topology, future features of the proposed topology, operating mode of the proposed topology, steady state analysis. I will show simulation result, and followed by conclusion and future work. Introduction. Unidirectional ultra-high gain DC-DC converter are gaining popularity and used in a numerous modern power electronic based systems like electric vehicles. In electric vehicles, battery level voltage and machine level voltage is different. For matching this to voltage, we require a high gain DC-DC converter. And if in case of regenerative braking, there also energy can be stored in the battery. So bidirectional converter can play a very crucial role. But now I'm going to focus for unidirectional high gain DC-DC converter. Low level voltage to high level voltage can be charged by using unidirectional high gain DC-DC converter. And in case of renewable energy sources generally generate voltage, suppose for 24 to 50, etc. But suppose grid voltage is up to 400 volt, a small DC microgrid. I'm talking about a small DC microgrid, 400 volt to 500 volt or 600 volt. So by using high gain DC-DC converter, this DC generated voltage through the renewable energy sources, it can be boost up to 400 volt to 600 volt, and it can be sent to the DC microgrid or AC microgrid by using the inverter. So high gain DC-DC converter is very useful, and it has also several advantages and applications like a UPS, island renewable energy system, etc. And two this is a typical diagram of two state energy flow. Introduction. Unidirectional high gain DC-DC converter can be categorized into two types, isolated and non-isolated. Isolated converter are preferred where the galvanic isolation and high voltage gain is required. Mm, in a transformer, primary and secondary can be separated by using galvanic isolation, and main advantage of isolated transformer is or isolated converter is voltage gain of the converter can be increased by just changing the number of turns, and but it has several disadvantages like it increase the size and cost of the system. Mm, and it increase the overall losses. System will be very bulky, and it suffer from the high voltage spike issues due to the leakage inductance. Relatively, there will be high efficiency. Uh, s- Relatively there will be low efficiency and result in high voltage stress across the switches. So far, non-isolated high-gain DC-DC converter is concerned, it is suitable for simplicity and low-cost applications, but it has also some disadvantage like it can't provide galvanic isolations, and conventional non-isolated converter have limited voltage gain. Non-isolated converter also can be categorized into two types: coupled inductor type and non-coupled inductor type. Coupled inductor type is preferred for where the high voltage gain is required, and in case of coupled inductor type, efficiency will be better compared to the isolated converter, and losses will be less compared to the isolated converter. So far as non-coupled type inductor is concerned, it is suitable for simplicity and low cost applications, and it has also some drawback like it can't provide galvanic isolation, and conventional non-isolated converter have limited voltage gain. Background and motivation: to overcome the drawback of isolated converter, a high gain non-isolated DC-DC converter can be utilized. Some existing high gain unidirectional non-isolated non-coupled inductor based converter with single switch are listed below. As it can be observed here, there are four inductor topologies. Topology in A, author it is published in 2020, and topology in B, it is published recently 2022. In both the topology, author has implemented LC2D network, and here it is implemented capacitor and inductor diode based some boost cell. Main advantage of these two topologies are by just adding this boost cell, voltage gain of the converter can be increased, but overall, it will increase the size and cost of the system. And if a system will have large number of component, also losses will increase. So these are the disadvantage, and both are unipolar. And converter both are unipolar, and converter in B author has used converter in B, C, and D. Author has used very large number of component. Maximum voltage stress across the switches and diode in B, C, D is very high, and all has unipolar structure. Gain in the converter B is more, but gain in converter B, C, and D is very limited when author has used very large number of components, as it can be observed. In continuation, some existing high gain unidirectional uncoupled isolated high gain DC-DC converter with dual switch are listed below here. In converter A, B, and C, voltage gain is limited, and in converter A, maximum voltage stress across the diode and switch is very high. It doesn't have a bipolar features, and total component is less here. This is advantage, but uh, it switches number of switches is more here. In topology B, author has used very large number of component to develop this topology. Number of switches is 2 here, and it doesn't have bipolar feature. Still voltage gain is limited here. Converter in C, voltage take across the switches is low here, but author has used very large number of component to develop this topology, and it has two switches. Still voltage gain is limited here. In topology in D, high gain DC-DC converter, and the advantage of this topology is voltage gain is very high, good, But disadvantage of this topology is author has used very large number of component to develop this topology. Number of switches is 2 here. Maximum voltage test across the switch and diode is very high, and this topology is lacking bipolar structure. Continuation, background and motivation. Observation from the literature survey. There are numerous converter with the very high voltage gain, but it achieved with the using a very large number of components. Somewhere voltage gain is good, but the voltage stress across the switch and diode is very high. And somewhere in the literature, high voltage conversion ratio capability, but it is achieved with the limited range of duty ratio. So these are the disadvantage. And conclusion from the literature survey: a high voltage gain unidirectional DC-DC converter with less number of switches, intermediate capacitor, low component stress, and simple control structure are not commonly found. So to overcome the above mentioned issues, a novel multi-stage ultra-high gain DC-DC converter with a LC2D network is proposed. This is the proposed topology, and I have developed this topology by using basic conventional boost converter. This is a boost converter, and I have incorporated here uh, s- some boost cell, and it can be observed in the green shaded part. So this is a boost cell I have incorporated here, and in place of inductor I have incorporated some capacitor inductor based boost cells, and because of this boost cells, overall voltage gain of this converter is very high. And here it can be observed this converter can be increased up to n according to voltage gain requirement. So this is the benefit of the main benefit of the proposed converter. These are the operating mode. During mode 1, all the inductor will store energy, and mode 1 indicate the on state, and during off mode, inductor release energy. This is a steady state equations. These equation can be driven when the main switches is on, and this all equation can be driven when the main switches of the converter is off. And using the voltage second balance, voltage gain equation can be found out. So voltage gain equation is 2 by 1 minus d ka whole cube, and this is a maximum switching stress of the converter, and which is been by 1 minus d ka whole square. This is a diode stress of the converter. This is a voltage stress across the capacitor. This is a current of the inductor diode 5, inductor L1, L2, L3, etc. This is a steady state waveform of the proposed converter. As I told earlier, during on mode, all the inductor store energy. During off mode, all the inductor release energy. And this is a diode waveform, diode current waveform. This is a capacitor current waveform of the proposed converter. I have also compared post converter with the existing high gain DC-DC converter, as it can be observed here in this table. So proposed converter gain of the proposed converter is 2 by 1 minus d ka whole is q, and maximum voltage stress across the diode and switches is Vn by 1 minus d ka whole cube. And so this column represent the proposed converter. Here I have incorporated here only one switches, 7 diode, 3 inductor, 3 intermediate capacitor, and the overall component is 14 only. And at 50% duty ratio, gain of the converter is 16 times of the input voltage, and it has also common ground features and bipolar capability. But in this table, I can observe at 50% duty ratio, proposed converter has 16 time gain, and in this table, all the converter has less gain. compared to the proposed converter, except converter in reference to it has same gain, but it has also some several disadvantages. Like author has used very large number of component to develop this topology, and maximum voltage stress across the switch is very high, and the maximum voltage stress across the diode is very high compared to the proposed converter, and also in converter in reference to it doesn't have bipolar features. So these are the disadvantage. This is a voltage stress versus topology plot, and here it can be observed. This is a voltage stress across switch, and there is a voltage stress across the diode. And here it can be observed in the reference to it has a high switching and diode stress compared to the proposed converter. This is a voltage gain versus duty ratio plot, and here in uh, figure A, it can be observed. Proposed converter provide best performance compared to the all references converter in all references, and in figure B, proposed converter has good voltage gain, but converter in reference to is better, but it has several disadvantages as I talked in this last slide. That has a large number of component, and also author has used means large number of component, and the maximum voltage across switch and diode was very high. So these are the disadvantages in the topology in reference to validate the efficacy of the proposed converter. It is simulated and designed taking the power rating of 300 watt, switching frequency 20 kilohertz, input voltage 24 volt, output voltage will come around 400 volt at 50% duty ratio, and these are the eq- equations, and voltage uh, current ripple can be calculated by using this formula. This is a steady state analysis, and these are the simulation result. During on mode, all the inductor store energy; during off mode, all the inductor release energy. And this is a diode current waveform: D3, D4, D2, D5, etc. And this is a capacitor current. This is the input output current, and here it can be observed. This is a desired output voltage of the converter, which is around 400 volt, near by 400 volt, and it is exactly 384 volt at which is 16 time gain of the input voltage. Input voltage is just 24 volt. Conclusion: a novel multi-stage ultra-high gain DC-DC converter with active switch inductor as LC2D network is proposed. The proposed converter support unidirectional operation and demonstrate low voltage stress across the various components. Maximum voltage stress across the switch and diode is low compared to the other high gain DC-DC converter. Proposed converter demonstrate high voltage conversion ratio, and it has simple control structure. Proposed converter was designed and analyzed in the detail for the power level of 300 watt. Detailed simulation results also provided to validate the theoretical design and efficacy of the proposed converter in open loop only. Proposed converter is found to be suitable for electric vehicles, renewable energy, portable, non-portable, medical equipment, PC microgrid, drones, and so on. These are the my future work. Closed loop control I will do, and analysis in DCM shall be carried out. Loss analysis and efficiency computation shall be carried out. Prototype development of the proposed converter for the experimental validations is in progress. For increasing the efficiency, soft switching can be incorporated in this converter. These are the references what I have utilized for the proposed converter. And thank you, everyone.